Hi everyone, we will continue with our chapter on operating system. We will continue with our topic on input-output bound and processor-bound jobs. M'apparaît quoi nous dire? Input bound, a lot of input and output, little processing. Processor bound, lots of processing, little input and output. Different types of program need different amounts of processor time. A program which is constantly recalculating matrix computations in order to display 3D graphics needs lots of processor time and is said to be processor bound. A program that runs a database query and is constantly having to read data records from a hard disk is said to be I/O bound. An operating system should give high priority to I/O bound programs, low priority to processor bound programs. Une façon de penser, puisque I/O bound process, for example, printing, nous vais donner plus beaucoup priority parce qu'elle est lente en comparaison avec processeur. Next, we will look at the objectives of scheduling. The objectives of scheduling are to maximize use of hardware resources, maximize throughput. Maintenant, question c'est what is throughput? Throughput is the amount of work completed in a unit of time. Next objective is to allocate resources fairly to all users. Resources, input, output, storage, the processor. Provide acceptable response time for interactive users. Maintenant, on veut connaître ce veut dire un interactive operating system. An interactive operating system is one that allows the user to directly interact with the operating system while one or more programs are running. Next, it should provide an acceptable turnaround time for batch users. That is, to meet the deadline for production of the final output. 6 objectives. It manages system performance. For example, temporarily increase time taken to respond if the system is overloaded. The last objective is to prevent deadlock. Deadlock is to wait for an event that will never occur. So you keep on waiting. Question: what factors must be considered when assessing if the objective can be met? The following factors must be considered when assessing if the objective can be met. Number 1, priority. Low priority to processor-bound jobs. High priority to input-output bound jobs. Second, type of job. Real-time processing must be done quickly so that the next input can be affected, like in monitoring and control system, temperature control, for example. Batch processing only has to meet the deadline for final outputs. For example, in the production of payslips, salary. The third factor is resource requirements. The amount of processor time needed to complete the job, the memory required, the amount of input or output time needed. The fourth factor is waiting time. The time the job has been waiting to be loaded into main memory. Ici, on a fait un récap de process states. Ready, running, blocked. Maintenant, navigate scheduling algorithms. The premier scheduling algorithm is first come, first served scheduling. Therefore, this is the simplest CPU scheduling algorithm. The process that requests the CPU first is allocated the CPU first. Même pareil, quand nous faisons la queue dans le supermarché, c'est qu'avant que tu aies, il ne peut pas savoir. OK? Ça veut dire, first come, first serve, est related avec nous queue structure. First in, first out principle. The data added to a queue first, on appelle ça processor NQ, adding data item to a queue, NQ, is the data that leaves the queue first. On appelle ça processor DQ. Suppose we have 4 processors, P1, P2, P3, and P4, with the following burst times. Alors, la dernière fois, nous venons avec ce terme-là, burst time. It refers to the time required in milliseconds by a process for its execution. Alors, process 1, 23 millisecondes. Process 2, 4 millisecondes. Process 3, 9 millisecondes. Et process 4, prend 3 millisecondes pour terminer son execution. Maintenant, on va faire référence au process state. Ici, nous prenons un ready queue. Donc, qui load, il peut execute moment process. Alors, t is equal to 0 au commencement, nous avons process 1 qui prend 23 millisecondes. 0 plus 23, 23 millisecondes. OK, first come, first serve. Next, nous avons process 2 qui prend 4 millisecondes. Process 2 prend 4 millisecondes. 23 plus 4, 27. Process 3, troisième, qui prend 9 millisecondes. 27, process 3, 27 plus 9, qui fait 36. Et process 4, qui prend 3 millisecondes. 36 plus 3, okay? 39. Il crée ça, ready queue, first come, first serve. Maintenant, ici, ce qu'il nous faut faire, nous faut calculer the average waiting time for a process. OK? Alors, nous get un coup. Comment nous gagnons ça? Process 1, au commencement, il est venu. Comment il venu nous donner processeur, c'est-à-dire, bien non important. Process 2, c'est seulement après 23 millisecondes qu'il y a un processeur il vient attendre 23 millisecondes. Process 3, après 27 millisecondes, troisième était dans la liste, et après 27 millisecondes, il y a là qui est pour servir processeur. Et process 4, à la fin, t is equal to 36, il y a là qui est un processeur. C'est après 36 millisecondes qu'il y a un processeur. Dans le tout, nous divisons par 4, nous avons 21,5 millisecondes. This is the average waiting time for a process in first come, first serve scheduling algorithm. Next, we get shortest job first scheduling and shortest remaining time first scheduling. Alors, nous trouvons que first come, first serve, this is the simplest one. Ce n'est pas nécessairement qu'il est effectif. Nous devons minimize the process waiting time. Et si nous rappelle, nous faisons le non-preemptive et preemptive. Alors, ce qu'on nous dit preemptive, veut dire nous sommes capables de prendre processeur, nous donner ça l'autre process. Et quand nous dit non-preemptive, nous ne sommes pas capables de prendre processeur, nous ne sommes pas capables de donner ça l'autre process. OK? Il est supposé terminer. Alors, shortest job first is non-preemptive. And shortest remaining time first is preemptive. Okay? The burst time, amount of time taken in milliseconds for the process to execute, the burst time of a process should be known in advance. We will consider the same for processes and burst times as in the example above. With shortest job first, the process requiring the least CPU time is executed first. Par exemple, ici, parmi ces quatre-là, we see that process 4 takes only 3 milliseconds. Second will be process 2. Third will be process 3. And last will be process 1. OK? Nous get ça quatre process là. Nous gettons parmi ces quatre-là, qui sont là qui prend moins les temps, pour prendre moins les temps pour les terminer son execution, pour les execute. Nous trouvons process 4. Alors, nous create and ready queue as this one. Alors, au commencement, nous avons process 4, then process 2. Process 2, nous connaissons qui prend 4 millisecondes, 3 plus 4, 7. Process 3, 9 milliseconds, 7 plus 9, 16. Et process 1, il prend 23 milliseconds, 16 plus 23, 39. Now we need to calculate the average waiting time. Alors, process 3, tout de suite, il gagne pour servir processer. Il y a là, il pas n'attendre, nous avons 0 millisecondes. Next, we have process 2. C'est seulement après 3 millisecondes qu'il y a pour servir processeur. Process 3, seulement après 7 millisecondes qu'il y a pour servir processeur. Et process 1, seulement après 16 millisecondes qu'il y a pour servir processeur. Nous ajoutons tout, nous divisons par 4, nous avons 6,5 millisecondes. Rappel, pour shortest, first come, first serve, okay? First come, first serve, nous calculate average waiting time de 21,5 millisecondes. Mais quand on peut servir shortest job first, average waiting time for a process infinity is 6,5 milliseconds. On veut dire shortest job first, shortest remaining time first, nous là, on peut servir to minimize the waiting time. With shortest remaining time first, the processes are placed in the ready queue as they arrive. Ça veut dire nous pousser bien time of arrival column. But when a process with a shorter burst time arrives, the existing process is removed. It is preempted from execution. OK? Alors, si vous voyez sur burst time, vous pouvez execute, mais si nous gagnons un autre process qui se burst time, le plus petit qui m'a déjà faire, pour retirer, pour donner un nouveau process qui a moins burst time. The shorter process is then executed first. Okay, let us consider the same four processes, but this time we're going to include the arrival times. Alors, t is equal to 0, process 1 inventing. T is equal to 1, process 2. Et si nous comparons ça de là, process 2 in a shorter burst time en comparaison avec process 1. Nous get no ready queue. Là, nous explique d'après ça. T is equal to 0, process 1 inventing. Nous execute li. Mais t is equal to 1, process 2 inventing. Nous preempted. Nous tier process 1, nous met process 2. Execute. At t is equal to 2, dans the tables updated, at t is equal to 2, time of arrival, t is equal to 2, process 3 inventing. Mais ce burst time li 9 millisecondes. Tandis que process 2, ce burst time li 4 millisecondes. Nous donne process 2 encore n. At t is equal to 3, process 4 inventing, but with a burst time of 3 milliseconds. Et plus tigit qui process 2, mo chiali, on met process 4. Me donne process 4 sur 3 millisecondes parce qu'après process 4, pénanoïa, me donne sur 3 millisecondes interminé. Et là, next qui était process 2 avec 4 millisecondes. Mon déjà fini d'un process 2, 2 millisecondes ici. Comme elle reste 4 et 2, 2, il reste 2 millisecondes pour process 2. Process 4 interminé, process 2 interminé. Maintenant, on va avec process 3 qui fait parce que process 3, il prend seulement 9 millisecondes. 8 plus 9, 17. On termine avec process 3. Quand process 3 infini, on get process 1, il prend 23 millisecondes. OK? Mais ici, nous avons déjà fini de 1 milliseconde. OK? 23 retient n, 22. 17 plus 22, 39. Nous calculons ça, average waiting time. Alors, premier là, 0, ça c'est pour process 4. Parce que comment process 4, tu viens à t is equal to 3, moi tu finis de donner processeur pour ça. Il n'est pas d'attendre non. OK? Je donner 0. Next, process 2. Process 2, il regagne processeur à t is equal to 6. Mais, il fait 1 à 3, vous avez dans le diagramme, vous avez dans le notes, process 2, tu gagnes t is equal to 1 to t is equal to 3. Tu gagnes 2 millisecondes. Là, à t is equal to 6, les regains processeur, les regains 2 millisecondes, il termine. Et tu regains processeur à t is equal to 6, à cause de ça, on va faire 6 minus 3. Process 3, il gagne processeur pour la première fois à t is equal to 8. OK? Mais il vient dans nos arrival time of process, nous trouvons qui? Process 3, il vient à t is equal to 2. Ça veut dire qu'il vient à t is equal to 2, mais il gagne processeur à t is equal to 8. Pour ça, nous fait 8 minus 2. Process 1, OK, au commencement, nous fini execute process 1 pour 1 milliseconde seulement. Là, il regagne processeur at t is equal to 17. À cause ça, nous fait 17 minus 1. On divise par 4, nous gagne 6.25 millisecondes. Alors, nous refaisons, nous summarize ce que nous avons expliqué pour shortest remaining time first. Process 1, P1, arrives first. But after only 1 millisecond of processing time, process P2 arrives with a burst time of 4 milliseconds. This is a shorter burst time than process P1, which is 23 milliseconds. Process P1 remaining time for completion is equal to 23 and 22 milliseconds. Is now removed and placed in the blocked queue. Process P2 is now placed in the ready queue and processed. As P2 is executed, process P3 arrives 1 millisecond later. Here, t is equal to 2. But the burst time for process P3 is 9 milliseconds, which is greater than the burst time for P2, 4 milliseconds. Therefore, P3 is put in the blocked queue for now, and P2 continues 1 millisecond. After another 1 millisecond, P4 arrives. T is equal to 3. This has a burst time of 3 milliseconds, which is less than the burst time for P2, 4 milliseconds. Thus, P2 remaining time for completion, ici, il gagne 2 millisecondes, 4 à 2, 2 millisecondes. Remaining time for completion is equal to 2 milliseconds. Is removed and out into the blocked queue. Process P4 is now put in the ready queue and is executed. Once P4 is completed, P2 is put back into the ready queue for 2 milliseconds until it is completed. Burst time for P2 is less than the burst time for P3, which is 9 milliseconds. P3 is now placed back in the ready queue because the burst time P3, 9 milliseconds, is less than the burst time P1, 23 milliseconds, and completed after 9 milliseconds. 8 plus 9, 17. Finally, process P1 is placed in the ready queue and is completed after a further 22 milliseconds. We come to our next scheduling algorithm, round robin. In round robin, entendre ce qui est important, okay, c'est quantum. It is a fixed time slice. A fixed time slice which is given to each process. What is a quantum? A quantum is a fixed time slice given to each process. Si nous faisons ce diagramme, ici, nous avons un quantum of 3. José, il y a un quantum of 5. C'est-à-dire, il prend 5 millisecondes pour terminer ce travail. Maria, il peut prendre 2 millisecondes pour terminer ce travail. Et Marc, il peut prendre 2 millisecondes pour terminer ce travail. Quand l'IPVIN servait ce système-là pour 3 millisecondes, quand ce 3 millisecondes est terminé, José va à l'arrière. Il reste 2 millisecondes. Et là, Maria, pour servir ce système-là. Il y a 3 millisecondes, mais dans 2 même, pour finir terminer ce travail. Il sortir en dehors système-là. Même pareil pour Marc. Il y a 3 millisecondes, mais dans 2 millisecondes, pour terminer ce travail. Et là, out of the system. Et là, José, qui reste 2 millisecondes, il pourrait servir ce système-là. Once a process is executed during its time slice, it is removed and placed in the blocked queue. Then, another process from the ready queue is executed in its own time slice. Nous donne ce terme-là, context switching. Context switching is used to save the state of the preempted processes. Quand nous prendre un travail sur time slicing over, nous garde ce state of the registers qui data se tenant, nous save. Nous avons context switching. The ready queue is worked out by giving each process its time slice in the correct order. The ready queue, we're going to talk more in that, giving each process its time slice in the correct order. If a process completes before the end of its time slice, then the next process is brought into the ready queue for its time slice. Avec Maria. Thus, for the same 4 processes we discussed earlier, P1 to P4, we get this ready queue. Alors, je nous rappelle, process 1, tu prends 23 millisecondes. Process 2, tu prends 4 millisecondes. Process 3, 9 millisecondes. Et process 4, 3 milliseconds. Ici, nous pouvons servir un time slice of 5 milliseconds. Quantum is 5 milliseconds. Process P1, commencement. Il y en a 23 millisecondes. Mais on donne seulement 5 millisecondes. 5 milliseconds. Ce time slicing over. OK? Fait 23 et 5. 18. Là, nous donne next time slice to process 2. Ce qui est intéressant ici, nous donne un time slice de 5 millisecondes. Mais process P2 is taking just 4 milliseconds. Nous donne 4 milliseconds. It's over. 5 plus 4, 9. We have completed the execution of process 2. Next, we have process 3. Process 3 is taking 9 milliseconds. The burst time for process 3 is 9 milliseconds. But we have a time slice of only 5 milliseconds. So 9 plus 5 is equal to 14. But we are not yet done with process 3. We have 4 milliseconds remaining. Process P1 and P3 goes to the blocked queue. Next comes process P4. The burst time of process P4 is 3 milliseconds. So it will take only 3 milliseconds. It is over with process P4 and process P2. Maintenant, nous trouvons qu'il nous a 18 millisecondes restés pour process P1. Alors, je me redonne process P1 the next 5 milliseconds. 17 plus 5, 22. OK? Alors, ça nous fait 18, 5, 13. Next time slice is over for process P1. Comes process P3. Process P3 nos diz a fini de 5 milliseconds. OK? Reste 4 milliseconds. On va donner 4 milliseconds. 4 milliseconds, 22 plus 4, 26. Process P3 is over. Maintenant, comment on peut trouver? Nous reste seulement process P1. OK? 13 millisecondes. On va donner n time slice 5 millisecondes. 26 plus 5, 31. Time slice over. On va redonner un time slice de 5 millisecondes. 31 plus 5, 36. On va redonner 3 millisecondes qui est resté. 36 plus 3, 39. Maintenant, ce qui nous fait pareil, nous vous calculer ça, average waiting time. Alors, process P1, ligne terminée, 39 millisecondes. OK? Mais nous trouvons process P1 in attend jusqu'à 23 millisecondes. OK? 39 retire 23, 16. Pareil pour process P2, ligne terminée dans 9, t is equal to 9, mais ligne attend 5 millisecondes. OK? Process P3, ligne terminée t is equal to 26, mais sur burst time T9. 26 retire 9, 17 millisecondes, ligne attend. Et process P4 ligne terminée à t is equal to 17, mais sur burst time T3. 17 retire 3, 14. Nous ajoutons tout, nous gagnons 13 millisecondes. The average waiting time for a process using round robin is 13 milliseconds. Alors, nous comparer, nous trouver first come, first serve, 21.5 milliseconds. Shortest job first, 6.5. Shortest remaining time first, 6.25. Et round robin, 13 milliseconds. Now we're going to talk about job status and the schedule. Refer again to the diagram. Ready queue, waiting for the processor to become available. When the processor is available, go to the running state. Time slice over, go back to ready. Waiting for input output, go to the input output block state. Okay. Setting terminate, termination. Job is moved into ready queue, and the position in queue is determined by priority of job according to rules laid down by the scheduler. Part of scheduler which loads jobs into ready queue is called the high-level scheduler. The high-level scheduler is part of the scheduler which loads job into the ready queue. When currently running job leaves running state, the job at top of the ready queue is loaded into process and run. This is done by the low-level scheduler. If a job requires If a job requires peripheral time, it is moved to the block state to await servicing. After it has been serviced, it must return to the ready queue to await its next turn to use a processor. The task of moving jobs between the secondary storage and the primary memory is carried out by the medium-level scheduler. The task of moving jobs between the secondary storage and the primary memory is done by the medium-level scheduler. Next topic. How the kernel of the operating system acts as an interrupt handler and how the interrupt handling is used to manage low-level scheduling. A kernel is a central part of an operating system. It manages the operations of the computer and the hardware, most notably memory and CPU time. A typical computer user never interacts directly with a kernel. It runs behind the scenes and cannot be seen except for the text logs that it prints. The kernel is the most fundamental part of an operating system. It can be thought of as a program which controls all other programs. Okay? It can be thought of as a program which controls all other programs on the computer. When the computer starts, it goes through some booting functions, such as checking memory. It is responsible for assigning and unassigning memory space, which allows software to run. The kernel provides services so programs can request the use of the disk or other pieces of hardware. The kernel forwards the request to special programs. The kernel forwards the request to use a disk, the request to use other pieces of hardware, forwards a request to special programs called device drivers, which controls the hardware. The kernel also manages the file system and sets interrupts for the CPU to enable multitasking. Many kernels are also responsible for ensuring that faulty programs do not interfere with the operation of others by denying access to memory that has not been allocated to them. Denying access to memory that has not been allocated to them. And restricting the amount of CPU time they can consume. The CPU will check for interrupt signals. The system will enter the kernel mode if any of the following type of interrupt signals are sent. First, we have device interrupt. For example, device interrupt. For example, printer out of paper. The device is not present. Second, exceptions. For example, instruction faults, such as division by 0, unidentified opcode, stack fault, and so on. Third, we have traps, software interrupt. For example, process requesting a resource, such as a disk drive. When an interrupt is received, the kernel will consult the interrupt dispatch table, IDT. Have a look at this diagram. This is an interrupt dispatch table. This table links a device description with the appropriate interrupt routine. Okay, interrupt service routine. The container and instructions to service a particular type of interrupt. SAC device also of interrupt service routine. The interrupt dispatch table will supply the address of the low-level routine to handle the interrupt event received. The kernel will save the state of the interrupt process on the kernel stack, and the process state will be restored once the interrupting task is serviced. Interrupts will be prioritized using interrupt priority levels. Forget interrupt dispatch table. Maintenant, le terme interrupt priority levels. It is numbered 0 to 31. The higher the value, the higher the interrupt. A process is suspended only if its interrupt priority level is greater than that of the current task. The process with a lower interrupt priority level is saved in the interrupt register. The process with the lower interrupt priority level is saved in the interrupt register and is handled. It is serviced when the interrupt priority level value falls to a certain level. Some examples of interrupt priority levels include, for example, the number 31, the highest, the largest, is power failure interrupt. Interrupt priority level 24, this is for the clock interrupt. And interrupt priority level 20 to 23 is for the input or output devices. If the operating system is to manage interrupts, the sequence of execution is modified. After the execution of an instruction, the processor checks to see if an interrupt has occurred. If so, the operating system services the interrupt. If it is more important than the task already being carried out. This involves running a program called the interrupt service routine, ISR. Every interrupt signal, for example, printer out of paper, has its own interrupt service routine that services the interrupt. Next question. How can the operating system arrange for the interrupted program to resume from exactly where it left it off? In order to do this, the contents of all the registers in the processor are saved. The contents of all the registers in the processor are saved so that the operating system can later restore them to carry on with the execution of the interrupted program. What happens if an interrupt occurs while another interrupt is being serviced? The simplest solution is to place the interrupts in a queue and only allow return to the originally interrupted program when the queue is empty. Here, is there an interrupt in the interrupt queue? Yes. Service the next interrupt. Keep on servicing the interrupt if they are of a higher priority than the currently interrupted program. The interrupts are held in a queue or the priority queue. The position of individual interrupts in the queue is determined by their importance. The more important the process, the higher the priority. For example, the user pressing Ctrl-Alt-Delete in the Windows operating system has a high priority, and pressing the computer's reset button has an even higher priority. The hardware within the CPU recognizes the interrupt requests, which is an electrical signal input on an interrupt line, and in response, the CPU sets aside the normal execution of events to respond to the interrupt. In most modern CPUs, what happens next is determined by a hardware handshake, particular to the type of CPUs, but most of them receive a number of the interrupting device. Every device has an interrupting number. That number can be 8 bits or 32 bits depending on the design of the CPU. The CPU then uses this interrupt number to index into the interrupt vector table. This is the table, the interrupt vector table. The CPU uses this interrupt number to index into the interrupt vector table to find an address to begin execution of the interrupt service routine. Chaque device a un number. Quand il y en a pour envoyer un interrupt, il envoie an interrupting number, c'est un number qui nous assign. Là, pour tel interrupt number, que ce interrupt service routine était, vous trouvez dans telle adresse. Ça veut dire même device est capable d'avoir différentes sources de problèmes. Chaque problème, c'est une source de interrupt. Et chaque interrupt, il y a une value, il y a un number. Alors, un type de interrupt in arrivé, il peut envoyer un number, de la tel number, il peut donner tel service routine de telle adresse. Once that address is determined and the current execution context is safely saved to the stack, the CPU begins executing the interrupt service routine. The sequence operations related to interrupt handling is shown in this diagram. We were executing the instructions, get an interrupt, you save the program status word, PSW, program status word, you save the return address. If you save the return address, parce que quand on finit termine execution of the interrupted program, okay, nous retourne dans nos previous program. Ça cause nous save the return address. Set PC to the vector address maintenant. You service interrupt service routine qui m'a instruction nous là. Quand on termine sa interrupt là, nous restore the program status word et PC ça va aller qui est gardé là, so return address et il continue sur instruction. Upon reception of the same, the general sequence of handling is as follows. Correct instruction being executed is completed. Alors, tout le temps, at least une instruction pour compléter, fetch, decode, execute, at least un cycle pour faire. Pas comme identifier fetch, fait decode, arrive un interrupt, il reste tout en place, non, il termine. The current instruction is being executed is completed. Parce que ça diffère in terms of nanosecond, picosecond. CPU copies an internal register called the program status word. The register that has the flags like carry, 0, okay, onto a stack. Address of the next instruction to be executed is saved on the stack so that it can be resumed after interrupt processing. The program counter is set to the vector address specific to that interrupt. A piece of code called the interrupt service routine is placed in the vector location of an interrupt to handle it. Now we are going to talk about the typical flow of operation. If needed, store the previous program status word and return address in memory. Store the context, any more internal registers, status registers, etc. that might be modified during the course of execution of this interrupt service routine. Perform necessary operations to process that interrupt, like copying data to, from the peripheral, prepare for next cycle. Upon completion, restore the context back to the original values from the stored values. Restore the process or status word, okay, the program status word, and jump to the address of the execute instruction next to the interrupted one. We will end this part here.